to the last lecture in this course, which is about presenting the counterexample to the telescope conjecture. But as usual, I have to finish up the discussion from last time first. So recall, if you have a spectrum whose homotopy in negative enough degrees is 0, then we had introduced this property QLN, which is that if you take x mod p v1 up to vn, then the homotopy of that is 0 for a star big enough. So really, because of this as well, that means that the homotopy lives in some bounded range. And then the main property was that if x has QLN, then maybe up to changing the Vn self-map, so raising it to a power, you can control the Vn periodic homotopy.
So in QLN, you assume that x...
Yeah, we'll only discuss this property when I already know that x is bounded below in homotopy.
Because it doesn't make enough sense otherwise, or you would think that there are only finitely many homotopies up to some n. You don't have to go further than like n plus 1 to determine a given homotopy.
Well, the thing is, I mean, if x is Vn periodic, then, well, I don't know. I mean, or if x is Vn minus 1 periodic. Like, for example, if x is rational, well, I don't know. That the Vn periodic homotopy is just the homotopy, this is n minus 1, mod pv1 up to vn, maybe raised to a power, made periodic. So more precisely, in some range of degrees, these two will be isomorphic, and then you know that this one is periodic, and then you can use that to transfer the information in all degrees from the information you have in that range of degrees. This is the property that makes it so that this, so to speak, telescopic homotopy, this Vn periodic homotopy of such a spectrum is actually accessible. You just do a bounded range of calculations and you get the whole Vn periodic homotopy. So it's supposed to be a nice property to have when you're trying to understand the Vn periodic homotopy of something. And so then we're interested in this for K of R, for algebraic K-theory spectra. And the classic situation would be, well, R is an ordinary commutative ring.
What does it mean, made periodic?
It means that first there exists, so Vn, let's say Vn has period d. So there exists a range of d consecutive homotopy groups where these are just isomorphic.
So you know that modulo that the Vn map is an isomorphism outside finitely many degree by QL.
Right. Yeah, but this one it's an isomorphism when I invert it, it's an isomorphism everywhere.
Okay.
Yeah.
Okay. Okay. So in other, but there. Okay. So what you are saying is that the reason A so that this gives it in some range,
exactly.
And then you make it periodic based on this range.
Exactly. So it's really a statement at the level of homotopy groups. It's important to understand. There's no way you can get the spectrum structure here from this, because, I mean, this is Vn inverted and this is modding out by Vn. They really are complementary. But somehow on the level of homotopy groups, you can still read off what's going on. Okay, so R is an ordinary commutative ring. X is like K of R, and we're looking at n equals 1.
From the proof of last time, like if you truncate, you can compare this to us.
If it's if you truncate, yes, yes, yeah. Right. So it's so the first regime is that if R lives over Z1 over P, then QL1 for K theory of R is broadly true. So you need some kind of finite dimensional assumption on R. I won't get into the details. Basically the same that you need for Thomason's theorem. And this is consequence of this Voevodsky, Beilenson-Lichtenbaum story. There's the complementary regime is when R is p-adically complete. And in this case, it's convenient to switch to TC. So there's a, well, so paper with myself and Keel Matthew and Matthew Morrow. So the fiber of, for such R is truncated. So the homotopy groups of this equals 0 for star large enough if R is finite dimensional.
When you refer to Voevodsky, I think in Voevodsky's work he looked at, he related K-theory and motivic cohomology like for things over a field, maybe small things, it's not so general.
No, yeah, so there are additional arguments you'd need, but not too difficult to go to the general case. Similar to as in Thomason's theorem. You use Nisnevich descent and essentially reduce to and Henselian rigidity, and you essentially reduce to a case of fields. Yeah. So this means that under again finite dimensionality, some kind of finite dimensionality assumptions, the QL1 for TC is equivalent to QL1 for K theory. And it's in principle easier to analyze TC than K theory, so it's profitable to make that switch. And I can't do justice to the whole historical discussion of this. I just want to say what the upshot is and list some names. So it's not broadly true. So in this regime here, QL1 for K theory or TC in general holds under regularity assumptions. But not in general. Oh, I forgot I'm supposed to be writing in script so you can actually read what I'm saying. But not in general. And so there's Buckstedt, Madsen, Hesselholt, maybe the most general result by Keel Matthew. So lots of work going into this. That's the upshot. So it's not quite as general. Quillen-Lichtenbaum is not quite as generally true as in this regime where you don't have any regularity assumptions, but you do need some kind of, so it's a little bit more of a specific phenomenon in the regime, in that regime there. But what we're really interested in is higher chromatic examples.
Do you have some EP counterexample for this?
Pardon?
Do you have some?
Yeah, so. Then, yeah. So that's Hesselholt-Madsen. They did you can calculate the TC, and it's so for rings where P is some power of P equals 0. So for example, for FP algebras, the V1 periodic homotopy vanishes. So the claim of Quillen-Lichtenbaum is just the claim that the K theory mod P or the TC mod P lives in finitely many degrees. And there it lives in infinitely many degrees.
Why is it Why does it say that QF says that this leaves a finely many degrees?
Because the V1 periodic homotopy vanishes. That was this purity theorem. Or well, in this case, it's more elementary, but. So yeah. So another way of reading this condition is that x mod p v1 vn minus 1 agrees with the thing where you invert vn in high enough degrees. So it's almost vn periodic. It's vn periodic in high enough degrees. So if you know the vn periodic thing vanishes, then it's saying that, right. So higher chromatic examples. So there's much less known in the higher chromatic story in contrast to these general soft theorems that we have, which say you have redshift basically always. This strong form of redshift satisfying this Quillen-Lichtenbaum conjecture, there's very few examples where we know what's going on. But there is one very nice family of examples where we do. So that's these spectra called BPN. So this is a certain ring spectrum. It's related to EN. This Morava E theory. It's of somewhat similar nature to EN. But it's not periodic, so its homotopy groups are polynomial. So it lives localized at P, our implicit prime, and then you have classes that you call V1 up to Vn, and they live in their correct degrees. So the degree of Vi is 2 times P to the I minus 1, which is kind of the correct degree for a Vi periodicity operator. And so to speak, Vn plus 1 equals Vn plus 2 equals dot, dot, dot. The next ones are all 0, is what you should imagine. Right, so for example, so BP0 is just HZP, or just ZP. BP1 is also something you can describe in classical terms. So you can take P-local connective complex K theory, so the non-periodic version, where you just have homotopy in non-negative degrees. That's 2 periodic. We want something 2 times P minus 1 periodic instead, which is a little more primitive. But you can get that just by taking the fixed points for the P minus first roots of unity. Well, let me p-adically complete to make it simpler to describe. So this is the kind of thing we've been considering, and this lives inside ZP cross, the P minus first roots of unity. So you take the fixed points here, and that actually makes you go from something 2 periodic to something 2 P minus 1 periodic. It's a little more primitive. And the higher BPNs are a bit harder to describe in classical terms. They sort of are what they are. Okay. So the theorem so this is Burklund-Hahn-Levy-Schlank when n equals 0 and p greater than 2, I think, and then maybe Rognes n equals 0, p equals 2. And now here's the big deal. Ausoni-Rognes n equals 1, and I believe p greater than 5. And then Hahn and Wilson in general. So TC BPN satisfies, I guess what you could say, strong redshift, or QL n plus 1. It's called Brown-Peterson spectrum. It's called truncated Brown-Peterson spectrum. Yeah. Yeah, I should. Yeah.
But there is something that they denote BP without.
Yeah, that would be if you had all the VIs up to infinity. That would be BP. And then this one's called truncated, where you force the VIs for I bigger than n to be equal to 0.
And does it depend on the choice? It doesn't depend on the choice of. Okay, so here the choice of these is very. Okay.
Yeah, so there is a subtlety in this, which is that in contrast to En, which is really an E-infinity ring, a fully commutative, this is maybe only E4. In principle, it's not. I think it's known to be E4, maybe Bastera and Mandel, and known not to be E13. So I don't know. So there's some. Yeah, that was Tyler Lawson. Anyway, but never mind these technicalities with how much commutativity you have. Right. So let me make a remark about this theorem.
And BP is a ring, is a full ring, or?
No, it's the same story with BP, yeah.
Okay.
Yeah. So remark for n equals 0 and 1, they actually give a full calculation of TC BPN mod P V1 Vn plus 1. For certain choices of these PV1 up to Vn plus 1, I mean these in this regime. So this was the big thing. This is the first example, really, of a higher chromatic redshift. This calculation of Ausoni and Rognes of TC of BP1. Right. And then another remark, I'm gonna put it on this board, even though it was supposed to be the previous board. So another remark is that, in fact, you have a stronger statement. There's something called TR. So this is something Hahn-Wilson show, and it comes from those calculations as well. This has QL n plus 1. And let me recall that, well, tell you that TC is related to TR in the following way. There's a Frobenius, so-called Frobenius action on TR, and TC is basically the fixed points. So you have a fiber sequence like this, so that this really is having QL n plus 1 for TR is stronger than having it for TC. And this is going to be very important for us. The stronger statement will actually play a big role in the disproof of the telescope conjecture, for reasons which I will discuss later. Okay.
And what is TR is something...
Yeah, so I'm gonna, through the course of this lecture, I'm gonna tell you more and more about these theories, TC and TR. I haven't said what they are yet. Okay, so I want to give a sketch of the proof of this theorem, so of following Hahn and Wilson. So I'm just going to sketch the TC, not the stronger thing. I won't tell you how to get the stronger thing from the same conclusion. But okay, now I need to tell you a bit more about TC. So there's the Nikolaus-Schulze description of TC. So you have TCR. Then there's something, the most primitive thing is THH. It has an S1 action, and you take the fixed points. And you can, there's also such a thing as an S1 Tate construction. And then there are two maps you can make here. There's the so-called canonical map and then the Frobenius map. And you take the equalizer of them, and you get TC. And the strategy is that mod P V1 up to Vn plus 1, you want that two things. The first thing, which they call Siegel conjecture. Never mind why it's called that. Phi is an isomorphism in high enough degrees. And the second thing, which they call canonical vanishing, so canon equals 0 on homotopy in high enough degrees. So you kind of split it up into, so this is clearly enough to get that TCR, well, modulo these things, vanishes in high degrees. Because you're taking basically the difference of an isomorphism and 0, so it might as well be an isomorphism, so the fiber would be 0. And it's nice to split it up into these two claims, because you can analyze them separately with different techniques. So for one, it's enough. So there's a more primitive Frobenius, again, defined on the level of THH. Satisfies that it's an iso in large enough degrees. Mod. Now here's an important point. You actually don't need to mod out by Vn plus 1 to get this claim. So that's stronger to say that you're an isomorphism in high enough degrees just when you mod out by P up to Vn. And it's good that the stronger thing is true because we don't have to worry about the whole redshift phenomenon, that Vn plus 1. We don't have to track where Vn plus 1 is in this. So that's the...
What is R here?
Well, R is BPN, yeah. Yeah.
Okay, so those things are defined for, you don't need complete commutativity.
No, you only need associativity. You only need E1. Yeah, thank you. Yeah. So Vn plus 1 is the subtle thing, because that's what's giving you redshift. Or to understand redshift, you really need to track Vn plus 1. That's the next height information. But these P up to V, PV up to Vn, we kind of already know what they are because they just come from R itself. They live in R itself. So so here we can ignore redshift. So don't need to understand. Don't need to track Vn plus 1. That's the goal here. And here the method is to put a filtration. So filter.
In the original claim 1, it's more P to Vn plus 1, right?
Yes.
But here it suffices to.
Yes, it suffices to do it mod Vn. If you get it mod Vn, then you can just take mod Vn plus 1 and you get the same claim mod Vn plus 1.
Oh, right,
Yeah.
I see.
Yeah.
Okay.
And it's important that the stronger thing is true. Yeah. So you put a filtration on this ring with associated graded. So a polynomial ring in like some where again this Vi is in degree 2 times p to the I minus 1. So it's a graded polynomial ring. Algebra over Fp. And then using this filtration, somehow you reduce to showing, reduce to considering this guy instead. So proving the same analogous result for this guy instead, where you replace these guys by these guys, and then that and then you do a direct computation, which was a Hesselholt when all generators in degree 0. So Hesselholt calculated all these Hochschild invariants for polynomial rings over a perfect field. And this is what they did in this paper here is some generalization where you have the polynomial generators living in some even homological degree instead of just living in degree 0. But it's very similar. Okay. So that's the Siegel conjecture. Now the canonical vanishing, the technique is different. So here we really do have to worry about Vn plus 1, but we don't have to worry about the Frobenius. So the canonical vanishing.
I think there was something else in homotopy theory that was called.
That's correct, and I will not explain the relation. There's a reason they're called the same thing, but I'm not going to spend time on it. Right, so for canonical vanishing, the benefit, the only bit of structure you need to consider is the S1 action on THH. You don't need the Frobenius. The drawback is you have to keep track of Vn plus 1. So the method is descent along. So you have, say, THH of BPN. And then, in order to better see Vn plus 1, you do a relative THH calculation instead. So there's this thing called MU, which I never explained, even though it's central to the chromatic story. But you can think of it as being like BP infinity. It's actually got extra junk, but it is E infinity, so that's good. Right. And then here you can see Vn plus 1 in the fixed points because Vn plus 1 is visible in MU. So now you have a Vn plus 1 to play with because you're linear over MU, and you can kind of detect that although Vn plus 1 equals 0 in THH, as you go up the tower giving you the homotopy fixed points, Vn plus 1 is no longer 0, but its square is 0 in the first step, and then its third power is 0 in the next step, and then so on. And eventually, it's not 0 at all. And in fact, you can invert it to get something non-trivial. Okay. But the point is, yeah, you do descent along this, and in this guy, you can recognize your Vn plus 1, and you can do enough of an analysis. I will not go into more detail.
You said something about Vn plus 1 becomes, the power becomes, yeah, I didn't catch this, that the power becomes bigger.
Yeah, so so there's for example, if you take Hochschild homotopy, the thing you want to think about if you want to get an understanding for this phenomenon is something like, say some relative Hochschild homology of K relative to K bracket X, where X equals 0 here. Well, this is a K module. Well, it's a K bracket X module, but on the Hochschild homology itself, it's also K linear, so X equals 0 in this Hochschild homology. But when you do Hochschild homology, and then you take the fixed points for S1, then it's not true that X, so X is not 0. And in fact, so there's a tower for building this up where you use the cellular filtration on BS1 or CP infinity, and you see more, and you see, like in the second stage, it's X squared that's equal to 0, but X is non-zero.
And then finally, X is not important in the full thing.
In the full thing, yeah. So yeah, so this is some kind of algebraic, so very vaguely an algebraic analog of redshift.
This computation is also related to derived the rank homology.
Yes.
So, and what do you mean by descent?
Well, this is a map of rings, and you can make some kind of, you can do like this guy, and then its relative tensor product over this with itself. And you can make some kind of Amitsur complex, and you analyze the associated spectral sequence for the and then you take homotopy fixed points at every turn, and then you make some analysis of the resulting spectral sequence and show that it degenerates fairly quickly.
And the action is of S1. Okay.
Yeah.
So what helps in this computation also is that everything is like polynomial rings.
Yes, exactly. So a key thing here is that this guy is actually a polynomial ring in even degrees, which makes the S1 fixed points easy to analyze because the spectral sequence degenerates. Okay. So let me now make this remark about why, so the importance of QLn plus 1 specifically for TR. So these theories TC and TR are built from THH. Well, so THH of A is some tensor product like this. And this tensor product's all over the sphere spectrum, plus extra structure. Called the cyclotomic structure. And in the Nicolaus-Schulze approach, this extra structure is so a cyclotomic spectrum, and implicitly I'm like working at a prime p. So is a pair X phi, where X is spectrum with S1 action, and phi is a map from X to the CP Tate construction. So CP sitting in S1 as the P torsion. And this map should be S1 equivariant. Where, so in principle, this one doesn't have an action of S1. It has an action of S1 modulo CP. But there's a canonical identification of that with S1 by the multiplication by P map on S1. So then it makes sense to ask that this be S1 equivariant. And that's kind of the structure that was in play here. Right. And then the key thing is a result of, so there's the Antio-Nicolaus.
So what is BS1 in found BS1 spectra? What is BS1?
BS1 is like the classifying space of S1.
But viewed as
an infinity groupoid. Yeah. So.
In some way.
Yeah, in some way. So for example, yeah, if you have an ordinary group G, and so by BG you maybe mean the category with one object in automorphism group G, and then a functor from that to a category would just be an object in that category with a G action. So it's the same story here.
Okay, but is it does it correspond to doing equivariant homotopy? So when you do equivariant homotopy, you can somehow make it so that something which is homotopy equivalence on the total, forgetting actually is not necessarily an equivalence in the, because you can kind of specify the fixed point.
Yeah, so this is not that. This is a thing where the passing to the underlying object does detect equivalences.
Okay, so it is not the one you discussed last time.
It's not the, it's not the one I in words mentioned last time.
Okay.
Yeah. Okay, so Ntio-Nikolaus, there exists a T structure on cyclotomic spectra inherited from spectra, via the conservative functor TR. 6. So the most naive underlying spectrum of a cyclotomic spectrum is just the X, where you forget the S1 action and you forget the Frobenius. But there is a different underlying object, which is this TR construction, which is some inverse limit of some towers TRN, where TR1 is X, and then you build some thickenings. Right, and this one has the nice property that you can use it to define a T structure on cyclotomic spectra. So an object here is connective if and only if TR as a spectrum is connective, and it's co-connective if and only if TR as a spectrum is co-connective. Right, so what this means
So does it depend on the P, the prime P?
Yeah, there's implicitly a prime P, and I should be looking at P-complete spectra and P-complete cyclotomic spectra.
Okay, and also it's P-complete.
Yeah. So if you have QLn plus 1 for TR, this is the same thing as saying, which is, sort of TR. There's unfortunate notation here. Sometimes you talk about TR of a cyclotomic spectrum, but then TR of a ring spectrum is TR of the cyclotomic spectrum given by THH. Right, this means that THHR mod P V1 Vn plus 1 is bounded in the Ntio-Nikolaus T structure. So the whole structure that you need to form TC, which is the cyclotomic structure, lives in a bounded range of degrees. Or I should say, the whole structure you need to form TC mod P V1 up to Vn plus 1. Okay. Any questions? All right, so now let's get to counterexamples to the telescope conjecture. So let me recall. This Devenitz-Hopkins tower. So we had the K1 local sphere, which is the same thing as the T1 local sphere. It has a ZP cross Galois extension, where at the top you find periodic complex K theory, P completed. And more precisely, this is encoded in this, what I was calling E1 so this is E1. This E1 Devnitz-Hopkins, which is a hypersheaf on the site of finite continuous ZP cross sets and of commutative ring spectra. So, okay, so then we have, so theorem, Ben Moshe, Carmeli, Schlank, Ben Moshe, okay, I have to, I mean, this is a dash in the name, so, yeah. Janowski. This is a collaboration, yeah? So if you take the K2 local K theory along this tower, or you apply K2 local K theory to this object viewed as a pre-sheaf, this is a hypersheaf. On this site. So this is in this case, this is the notation for the site of finite ZP cross sets. Sort of encoding the finite subextensions of this infinite Galois tower.
So did you define LK2?
Yes, I did. So this was remember that the telescope conjecture was the claim that if you have something T2 local such that you tensor with Morava K theory, K2, you get 0, then your original T2 local spectrum must be 0.
Okay, you discussed this boosted localization.
Exactly, and this is kind of a localization, so to speak, forcing the telescope conjecture to be true. So that the telescope conjecture is the claim that LT2 equals LK2. Yeah. And then the second half, so this is Burklund-Hahn, Levy, Thomason-Schlank. If you take LT2 K theory of this exact same object, this tower here, this is not a hypersheaf. And the corollary is that LT2 is not equal to LK2.
Yeah, and you said before that you can consider that ZP cross is like a quotient of something bigger. So it was.
Oh yeah, that was at higher heights. At higher heights, it's not ZP cross that you have here. It's this so-called Morava stabilizer group related to units in a division algebra. But there is a ZP cross quotient of that, and I'll discuss this in more detail presently. Okay, so first I want to just give in preparation, I want to give a quick background on hypersheaves. So, and in the context, so will G be a profinite group of finite virtual cohomological dimension, and then BG is the same site of finite G sets. So Akil, Matthew, and I studied this question of sheaves versus hypersheaves in some detail in an article of ours. And let me just give you the most important conclusion for the purposes of the story. So theorem, Clausen, Matthew. If you look at the hypersheaves of spectra on this, which is a full subcategory of ordinary sheaves, has a lot of closure properties. Well, it's obviously, if you look at the definition, it's obviously closed under limits, but it's also closed under colimits. And more importantly, it's closed under tensoring with F for any F which is just a sheaf. So if you have a hypersheaf and you tensor it with a sheaf, it's still a hypersheaf.
And you tensor it component-wise?
No. Tensor a sheaf in the category of sheaves.
Okay, you sheafify the tensor.
Yeah.
So you are saying smashing.
Yeah, this is we said that this means that this is a smashing localization of this. So in fact, it implies that hypersheafification is just tensoring with the a single object, like the hypercompletion of the constant sheaf on the sphere spectrum.
So in particular, if the unit object is a hypersheaf, then every sheaf is a hypersheaf.
Correct. Yeah. So let me say in particular. In particular, a module over a hypersheaf. A hypersheaf of rings, is a hypersheaf.
Okay, so you can resolve a module by tensoring like the usual.
Yeah, or even simpler. It's if M is a module over R, then M is a retract of R tensor M, by the unit and the action. Yeah, but okay. However you want to argue. So for example, if you're doing ordinary algebra, there's no difference. If you're doing some kind of purely algebraic sheaves, even in the unbounded derived category, they always satisfy hyperdescent. And the reason is, by the claim, it's enough to prove that the constant sheaf on Z is a hypersheaf, but the constant sheaf on Z is truncated, so it has to be a hypersheaf whenever it's a sheaf. So the hypersheaves, it's only relevant when your homotopy goes all the way up to infinity. So anything truncated is automatically a hypersheaf.
Okay, it's important that the cohomological dimension is.
Yeah, here it's important that the cohomological dimension is finite. Yeah. The way we prove this is by giving a criterion for being a hypersheaf, which basically says basically provides a formulation for the idea that a sheaf is a hypersheaf when there's like a uniform reason why the sheaf property is satisfied at a finite level. So, like when you have a sheaf, then you have some finite level descent condition, and there's maybe some complexity in how that descent happens. But if the complexity is bounded uniformly in the finite extension, then you're a hypersheaf, and conversely. To maybe illustrate this, let me give let me also give an example of a sheaf which is not a hypersheaf. So let's take Kn underline, the constant sheaf. Let's say, so even for the simplest group you can imagine, so ZP, cohomological dimension 1, extremely simple. You take the constant sheaf on Kn, on Morava K theory, Kn. Then the claim is that, so recall that like pi star Kn is like, say, fp to the n, and then maybe even degree 2, depending on your conventions. Right, so the claim is that if you take Kn, the constant sheaf on Kn and you take global sections, so that's supposed to be the thing that sits at the bottom of the tower, then this is calculated by a single iterate of the check construction. So let's say k greater than or equal to 0, take Kn, and then you take the fixed points for constant action of the quotient group Z mod pkz. So this is the claim that you just do the check construction just once. So in general, if you want to sheafify, you take your pre-sheaf and you do a check construction, and then you do it again and again and again and again, maybe even transfinitely in this setting, and then eventually you'll end up with a sheaf. But the claim is that for this one, you only need to do the check construction once, and it's already a sheaf. And that's basically because of Tate vanishing. Because the reason it might not be a sheaf would be because you have a fixed points here, which doesn't commute with a colimit. But by Tate vanishing, the fixed points is also an orbit, so it does commute with a colimit.
The fixed points is also... okay, you mentioned this.
Yeah, so that's a consequence of Tate vanishing. Yeah.
But here the Tate cohomology vanishes.
Yeah, exactly. Yeah. Yeah. Right. So, and then you can analyze on pi 0. So this is going to be even periodic, and I kind of already explained what this guy is. I explained it for Morava E theory, but it's the same for Morava K theory. So it's just functions on the, you have this Honda formal group, and you look at its full P infinity torsion, and you look at functions on that. And this is infinite dimensional. So, on the other hand, if you take the hypercompletion of this...
No. Do you take that, because this is a direct limit of thing, and the formal group is like inverse limit of some. No. Oh,
I'm sorry. Yeah, you're absolutely right. I apologize. It's on the tape module. Yeah, I'm so sorry. Thank you. Yeah. Yeah, thank you. You take the tape module instead. I mean, the inverse limit of the, thank you so much. Yeah, you take the inverse limit of the, yeah, on the level of O, it's a direct limit. Yeah, thank you so much. That was wrong. Yes. Yeah. Okay. On the other hand, this guy, and for hypersheaves, the global sections is calculated just like as if this were the discrete group Z. So like just like the group cohomology of ZP. So there's just a fiber sequence with 1 minus the generator, and this is acting trivially. well, not that that's so important for the argument, but so the homotopy of this guy is finite dimensional. So it's going to be, there's going to be a similar phenomenon in this theorem, that one way of giving the reason why this is not a hypersheaf is that its homotopy groups are going to be infinite dimensional, or at least one homotopy group will be infinite dimensional. Whereas for the thing at the top of the tower, the homotopy groups are all finite dimensional. And that contradicts the hypersheaf property. Okay, let's take a 5-minute break. So now I would like to prove the hyperdescent theorem for K2 local K theory. And this involves a very cool idea, which is the idea of higher cyclotomic extensions. This is, so Craig Westerland kind of did it in the KN local context, and then Carmelli, Schlank, Janowski did it in the telescopic setting. So the usual cyclotomic extension it's a ZP cross Galois extension of, say, Z1 over P. And it actually also works, or S1 over P, but no, okay. Let me not focus on that. And how can you build it? Well, so Z1 over P, and then you're supposed to adjoin a primitive P to the kth root of unity. And one way to get this is you take the group ring on the cyclic group of order P to the K. This is the group ring. And then you identify a certain idempotent, EK, and I'll put 0, because we're at height 0. This is a certain idempotent. Which picks out the primitive P to the kth roots of unity from the arbitrary P to the kth roots of unity. And then this is, by functoriality, basically, this has an action of Z mod P to the KZ cross. And that's the kth level in the cyclotomic tower, which I'll now be calling the 0th cyclotomic tower, so 6, 0. Okay. And what about at height 1? So the height 1 version. So this is going to be a ZP cross Galois extension of the T1 local sphere. This is, you think of this as the T0 local sphere, and you go to the T1 local sphere. And again, what you can do, and this is kind of fun. Now, instead of taking the group ring for Cp to the k, which would not give you a Galois extension, you take the group ring for B CP to the K. And then it turns out this does give you a Galois extension. And there's another idempotent that you can write down, which cuts out a primitivity condition. And this is the height 1 cyclotomic tower. And then there's a theorem from these guys. If you K1 local, okay, I'm going to write it like this. So actually the telescope conjecture is true at height 1. So K1 localizing doesn't do anything when you're T1 local. I should implicitly, I'm T1 localizing this whole thing. Well, I guess it doesn't. Yeah, I guess it's already T1 local, depending on how you parenthesize this. Yeah, maybe just, there we go. Recovers. So it is a ZP cross extension of the K1 local sphere, and it's actually the same as the one we were interested in from the beginning, this E1 Devenitz-Hopkins. So example, so if you take the colimit over K of this LK1 sic 1, and then maybe K1 localize at the end, well, then you get, there's some infinite level idempotent acting on, so LK1, there's some infinite level idempotent acting on now the group ring of CP infinity. So to speak, or really, well, and this actually, this actually turns into sphere bracket BCP infinity. After P completion, it's just applying an idempotent is the same, always the same as inverting the complementary idempotent, and in the infinite level, you're getting the bot element, and this is just Ku after P completion by Snaith's theorem. So at the top of the cyclotomic tower, you're recovering a description of complex K theory given by Snaith, where so a priori for complex K theory, you need vector bundles of arbitrary, complex vector bundles of arbitrary dimension, but this, which is p-adically the same thing as BU1, is just the rank 1 vector bundles, the line bundles. If you just throw those in and enforce spot periodicity, you get all of Ku. So that's kind of what's happening at the top of the tower here, but in fact, the claim is true at all levels of the tower.
So what's inside the limit? So in this example, so you put the colimit.
This here?
Yeah.
So I have this sic1, which is this tower of Galois extensions of the T1 local sphere. And I K1 localize it, which doesn't actually do anything, but
It's like, should be sec1 K.
Sec1, no, yeah, no, I said kth level of, oh, thank you, yes, yeah, thank you, yes. Ah, that was the issue, yes. Yeah. So I'm trying to look at the underlying, I'm trying to look at what's at the top of the tower here.
Wait, but in the theorem it says, it's not that this E1 DH is the top of the tower.
Well, E1 DH is the object encoding the whole tower. And at the top of the tower is E1. That was my notation.
Okay. Then E1.
And E1 is KUP completed.
Almost a proof.
Almost a proof, exactly. It's almost a proof, yeah. You have to keep careful track of these idempotents. That's the part that I'm going to be sweeping under the rug in this whole discussion, is keeping track of the idempotents.
Okay. You said that you don't need to apply, no, LK1 is needed, though, because you already use L.
Yeah, you don't need, well, first of all, if you put LK1 here, you don't need to put it here. Yeah. But also, you never need to put LK1 because the telescope conjecture is true at height 1. So I could write LT1 instead, and it would be the same. Okay, what about height 2? Well, it's a ZP cross extension now of the T2 local sphere. And you get it in a very similar way. You have a idempotent acting on a group ring, but now you have to take the double classifying space of this abelian group. And then you get the kth level of the cyclotomic tower at height 2. And there's a theorem identifying this. After K2 localization, then you can, so to speak, kind of calculate it, because K2 localization is calculable. Well, it can't be the full Devenitz-Hopkins tower at height 2, because that's not a ZP cross extension. That's a extension which is Galois with a much bigger Galois group. But it's a sub-extension. So F, this Morava stabilizer group. This is induced by an explicit surjection. From G2 to ZP cross. Such that, so if you look at the units in the division algebra, which is the subgroup here, this was a semi-direct product of group of order 2 acting on this, then this is the reduced norm on the division algebra. So it's a ZP cross sub tower of this Devenitz-Hopkins tower at height 2. Okay? Now recall the redshift philosophy, which says that height n information, when you apply K-theory, should go to height n plus 1 information. So one can ask how this plays out for these cyclotomic towers, and that's the story of cyclotomic redshift. So this is Ben Moshe, Carmeli, Schlank-Janowski. Yeah, I guess it was Bott and Clausen and Matthew for n equals 0. So they're generalizing some classical result. So if you take the Tn plus 1 local K theory along the height n cyclotomic tower, so that's what redshift tells us we're supposed to be considering, well, you basically get the n plus first cyclotomic tower, except, well, it can't really be that, because at the bottom of the tower, you're supposed to have the K theory of the Tn local sphere, not the Tn local sphere itself. So you just make a base change. Oh, Tn plus 1. No, Tn, yeah. And then, so there's a parameter k here, which you should maybe is implicit. So yeah, so maybe e.g. So that in this case, if you take the T1 localization of K theory of Z1 over P, and then you add all the P power roots of unity, so we go to the top of the tower. This is the same thing as the T1 local K theory of Z1 over P tensor Ku. And then so there's very similar statements of Steve Mitchell. Okay.
So here, so I take K of a sheaf is like taking it as a pre-sheaf?
Just take it as a pre-sheaf, exactly.
Is that automatically a sheaf?
Yes. That follows from these results, these descent results of CMNMs.
But you need to localize to...
Yeah, and we did. Yeah.
And K is the K. Okay, K is the equivalent, like the...
perf, it's based on perf, yeah. Yeah. There is an aspect that I didn't discuss where you need to actually, to do the descent, to prove the K-theoretic descent results here, you need to actually switch from perf to something else, and then use a redshift result to show that the difference doesn't matter from the after telescopic localization, but let's not get into the details of that. It's a correct statement when you just take perf. The proof has a detour, but it's still a correct statement when you just take perf.
So you say that K theory satisfies descent for finite étale, no, under some condition, after applying LT, it applies...
Yeah, if you have a Tn local Galois extension, then when you take Tn plus 1 local K theory, you get descent.
If you have
a Tn local Galois extension of Tn local E infinity rings, then when you take Tn plus 1 local K theory, you get descent.
And what does it say for usual rings?
Same thing. I mean, same thing. Same thing is true for usual rings.
So for finite étale extension,
yeah, for finite étale, for example, you get descent. Yeah.
you get descent for after LT.
After LT1, or actually after, but also after LTN for any n, but those vanish, so you don't really care.
Okay, and you don't need the negative K theory for this descent. It's just the perf based.
Yeah, I mean, again, we're doing telescopic localization, so it doesn't matter whether you include the negative K theory or not. Yeah. Okay, so a corollary is that Lk n plus 1, if you take Kn plus 1 instead of Tn plus 1, K theory of the nth cyclotomic tower, this is a hypersheaf. On BZP cross. And then the proof of that is that it's a module over, well, I should have said the pattern continues. Yeah, I only discussed height 2. Yeah, height n analogous. It doesn't stop at height 2, yeah. And the proof is it's a module over this this guy, which is a hypersheaf. Yeah.
His equivalence is based on redshift of Algebraic K theory?
This one here? In a way. So let me give the sketch of proof. Proof sketch of the theorem. So of the cyclotomic redshift. So the claim you want to make is that for all, say d greater than or equal to 0, LT1 k of r bracket b to the d c p to the k and k greater than or equal to 0. LT, sorry, n plus 1. And then R is Tn local. That this, when you take the K-theory of the group ring, it pulls out as an orbit. So so this is orbits, homotopy orbits for the trivial BDC p to the k action. So this is some kind of codescent.
Is it because of the shifted coordinate commutation?
Yeah, this is codescent. Now note, here's where the shifting is happening. So the homotopy colimits for the trivial action is the same thing as taking the group algebra with an extra b. Group So for example, the homotopy orbits for CP acting on something with a trivial action is just the homology of BCP. So there's an extra b, and it's similar all the way through. So you pick up an extra one of these. And then you're basically done, and then you keep track of idempotents. Done. Of course, that's where all the technical work happens, is in keeping track of these idempotents. And this uses semi-additivity. In fact, this whole story is based on semi-additivity machinery, which was in the K and local context, Hopkins-Lurie, and then these guys extended it to the T and local context and developed it further, and that's the key technical collection of results and ideas that goes into this, but it's not occurring at the level of this sketch that I'm giving you guys, so you can ignore it if you don't know what it is. Carmeli-Schlank-Janowski. So the cyclotomic redshift, after keeping track of idempotents, reduces to this codescent claim. And for this codescent claim, so the proof of claim, so it's an induction on D. So when D equals 0, it's basically this, well, we proved, I discussed descent. This is codescent, but the same set of techniques used to prove descent also prove codescent. And we did it in the paper, so that's all fine. And then for D bigger than 0, use that, B to the D plus 1 CK is some geometric realization of product of copies of, just using the usual bar construction, product of BDC to the K, and then commutation of LT plus 1 K theory with shifted colimits. So it actually reduces to the D equals 0 case. Okay. So the corollary, right, was that our half of the disproof of the telescope conjecture. It's that K2 local K theory does satisfy hyperdescent along this Devonitz-Hopkins tower at height 1. So is a hypersheaf. All right. But now why is T2 local K-theory not a hypersheaf? Oh, wait, that was what I just wrote. I should be going over here. By the way, I said you can just calculate to prove these kinds of theorems, but the calculations are not actually easy. They were done by Ravenel and Wilson, I think in the 90s or 80s. Relevant calculations are difficult. Okay, so theorem, and this is the Burklund-Hahn-Levy-Schlank, the other half of the disproof of the telescope conjecture. I'm not going to do their work justice. I'm going to state a special case of what they really prove, and even in that special case, I'm going to give a much weaker conclusion than what they actually obtain. And also in my sketch of proof, I'll be, omitting many details. But I just want to say just enough kind of to explain why the telescope conjecture fails, at least in one instance. So I apologize to these guys. So I'm going to take P odd, and I'm going to take R to be this BP1 with a P completion, which, and then I'm going to take the orbits for mu P minus, oh no, that was the orbit, sorry, which is KU P completed and the orbits for mu P minus 1. Now, acting on this group is ZP cross modulo mu P minus 1, which is ZP. And I'm going to think of that just as a Z action given by so I choose a generator for ZP, go through this, and I view that as acting on this ring, just a Z action on this ring given by that generator. No, fixed points. Did I say orbits? Oh, I meant fixed points in any case. Yeah. And then I'm going to take A to be the connective version. So this is called the atom summand. So that's why I'm calling it A. So then R. So R is tau greater than or equal to 0 of A. Okay. So the claim is that for large enough integers k, there exists some degree star in Z such that when you take the T2 local, well, let me say, if you take K theory of A and then the fixed points for P to the K times Z,
KU and big KU means the small KU is as a connective.
Exactly. Small KU is connective, big KU is periodic. Yeah. So the V2 periodic homotopy at the kth level of the tower is infinite in some degree. So this this implies that hyperdescent fails because pi star at the top of the tower, if you take just the atom summand, is degree-wise finite. That was the Ausoni-Rognes. Hahn-Wilson, maybe at smaller primes. So at the top of the tower, you get something finite homotopy. At near the bottom of the tower, at some finite stage in the tower, you get something with infinite homotopy. So you can't be a hypersheaf, because for a hypersheaf on ZP, at each stage of the tower, just sit in a fiber sequence with 2 copies of the thing at the top of the tower. Yes?
Use the logic of the previous one. In this K2 local K theory being.
Oh, yes.
So this, I mean, the proof is just saying that it's a module over this thing.
Yes.
And this follows from this cyclotonic redshift you're saying.
Correct.
But why does it not apply to T2 local?
So the key fact, so this Tn local, Tn plus 1 local cyclotomic extension, it is what it is. We don't have any other, we don't have an alternate expression for it. It is what it is. But once you Kn plus 1 localize, then you can identify it with a piece of this Devnitz-Hopkins tower.
And with this description, this redshift thing, you can further, okay, you can use the right-hand side to say that it's a module.
Exactly.
Okay.
Exactly. Yes. Okay. Okay, so the key is to find some infinite homotopy. This is, by the way, this is really a caricature of their results. It's not. I've already given apologies about that. The key is to find some infinite homotopy at some stage in the tower. Okay? Yeah. Yeah.
That's fixed points for p to the k.
Exactly. Yeah. I mean, it has to, actually, once you know this holds for some k, then it actually has to hold for k equals 1. But the argument goes via some k. Okay, so, yeah, so proof. So the step 1 is to switch from k of a, k of a p to the kz to tc of r p to the kz. So that's, so. So we have this connective guy, then we take fixed points, and we use TC instead of K theory. And of course, this is going to go through K of R, P to the KZ, mod P V1, V2 inverse. So that's where the natural maps are, yeah. If this guy were connective, this would follow from these general soft results I discussed, that at heights greater than or equal to 2, the K theory of any ring is the same as the TC of its connective cover. But this guy is not quite connective. This has homotopy in degree -1. So pi minus 1 is ZP. It's not 0 in any case. So we can't apply those general results. But this was fortunately, well, this is one of the other main, no, sorry, not Hahn-Levy. This is one of the other main, Ishan-Levy in a previous paper showed that nonetheless the conclusion is true. That even though this isn't quite the connective cover of this, because there's something in degree -1, you still can run similar arguments, again based on these excision results of Lond and Tama to get the same conclusion. So, okay. And it's really important to work with this R P to the KZ, which has this homotopy in degree -1, and not its connective cover. Its connective cover, the TC, is much more difficult to analyze, and probably the Quillen-Lichtenbaum property doesn't hold. So this brings me to the next step, I'm going to put it in quotation marks. So step 2, so for k large enough, we have QL n plus 1 for TR r p to the kz. I guess it's QL2 in this case, yeah. QL2 for TR r p to the kz with uniform range. Of degrees. So QL2 means your homotopy of something lives in some bounded range, and I want it uniform in all possible k. Large enough.
And also the SP plus condition should be uniform, or not?
Well, I mean, this guy is going to be yeah, it will be automatically, because yeah, no, not automatically. It's another thing that Levy showed, I'm sorry, that also the THH, in principle, when you take THH of something that's not quite connective, then it could become worse, but he showed that it doesn't in this case. So in the situation where I have a homotopy fixed points for a z action on something connective, when you take the THH, it stays bounded. And then the TR also stays bounded in terms of the THH. So it's not something you need to worry about. Okay. Right, so this is based on QL2 for TR of R, which is BP1. But this is like, it's a lie to call it step 2. It's really like the technical heart of the argument, and you have to do a lot of preliminaries to get this. So the deduction of the Quillen-Lichtenbaum property for this fixed points from the Quillen-Lichtenbaum property for R itself is actually one of the main technical points in the paper, one of the most difficult things to do. But I'm not going to say any more about it except this. And then step 3 for k sufficiently large. Sorry. Well, let me say, let me include another step. So enough to show. So by Quillen-Lichtenbaum property, it's enough to show that TC of this R p to the kz mod p v1 and then v2 to the a is infinite in some degree. So this is using this Quillen-Lichtenbaum property again. So instead of analyzing what happens when you invert V2, now we're reduced to studying something which lives in only a bounded range. If we find infinite homotopy there, then then we also find it when you invert V2. And then the step 4. So for k sufficiently large, this TC of R p to the kz mod p v1 v2 to the a is actually isomorphic to TC of R. I'm going to write it like this, b p to the kz. Apologies for the strange notation. So this means fixed points for the trivial action. So what we're going to do in this step is we're going to trade this non-trivial action, essentially by Adams operations, for a trivial action, which will be easier to analyze. And the idea of this is that both are finitary, are determined by finitely many data. Once you equip them with the correct structure, finite data, both, so, or both, let me say both THH of R p to the kz mod p v1 v2 to the a and THH of the trivial guy are determined by finite data as cyclotomic spectra with an action of the appropriate ring, so with an action of THH of so there's, for any homotopy fixed points, you're in module over the homotopy fixed points of the trivial action on the sphere. So, and then this is basically by the Coulomb-Lichtenbaum property. So you live in finitely many degrees. You also can prove an overall finiteness property, some kind of FPN plus 1 property. So you're in finitely many degrees, and each of those is of some finite amount of information. Right, so that they're each determined by finitely many data, and they agree in the limit as k goes to infinity because they're fixed points of the same object. And then that means they agree at some finite stage.
But you wrote the same. I don't understand. You wrote both. You wrote the same.
Both this guy and this guy, they're not the same because here I have fixed points for this non-trivial action, and here I have fixed points for a trivial action.
Okay. And then BP. Why write BPK? Is it the same as the mapping space?
Yeah, it's the same as when you take the fixed points for a trivial action, it's the same as the mapping space from the classifying space of the group. So that's why I'm writing it like that.
Okay, so determined by finite data, but you have to know determined by k. How this data changes with k.
Right, so but it's uniform also in k. Or at least the range of degrees is uniform in k.
So when you agree in the limit, you somehow can descend it to
yeah. Yeah. Yeah, this is one of the key ideas. Maybe I've said that phrase too many times. Maybe it's lost meaning now. Yeah. Okay. So then we're reduced to showing so now that we've passed to a trivial action, the p to the k doesn't matter. I mean, when you're passed from z to p to the kz, you're not changing the fact that the action is trivial. So we're reduced to showing that tc of r bz, just trivial z action on r, mod p v1. And I can actually again pass to, by same kind of Coulomb-Lichtenbaum. I was supposed to be analyzing mod v2 to the a, but now I go back to looking at the periodic version using Coulomb-Lichtenbaum again, that this is infinite in some degree. So use. And the argument for QLn plus 1 given here in step 2 also applies to the trivial action, which is why I can do this. Okay. And now, so now we analyze oh, what am I? Step 5. So analyze. THH of RBZ. Well, actually, I'm sorry. I'm not. So, in fact, I'm going to do something strange. So, it's even enough to show we're actually going to analyze the fiber of the comparison map. Oops. Again, mod P, V1, and then V2 inverse. Oh, boy. I apologize. Just the same thing here is written there. Is infinite in some degree. Because, again, this Quillen-Licht by this Ausoni-Rognes, we know that this is the same as this. So I'm just saying that we already know that this is finite. So this guy being infinite is the same claim that the fiber of the comparison map is infinite. So now so we analyze this comparison map of cyclotomic spectra. So note, so THH RBZ. So what is this? This is just a circle. So on the level of underlying spectra, this is just R direct some desuspension of R, the cohomology of a circle. And that should tell you that this is THH of R tensor, the spherical cochains on the sphere spectrum. And then THH, basically from its definition, is symmetric monoidal. So this is the same as THH of R tensor THH of the sphere spectrum. And similarly, THH of R BZ is the same thing as THH of R tensor sphere BZ, but that's also the same thing as THH of R tensor THH of S BZ, because THH of S is S. It's the unit object in spectra. Now, whoops.
Why the tensor quality?
Which one? This one here?
No, in the second.
This one? This one?
Similarly.
Oh, it's exactly the same as this. So it's because taking BZ is just taking x to the BZ for any x is just x direct some desuspension of x.
And what is THHS?
THHS, its definition is the Hochschild homology of S relative to S, but that's just S. Right. So, what's the conclusion from this? So if you take the fiber of THH R BZ going to THH of R to the BZ, this is isomorphic as a cyclotomic spectrum to THH of R tensor, the fiber of THH of S, SBZ going to THH of S BZ. Excuse me? Oh, thank you, yes. Okay. Now this was analyzed by, so this is the key thing where we're going to see infinite stuff pop up is in analyzing THH of S to the BZ. This was analyzed by Malkovich and then Levy-Levy. And these guys in this paper, this telescope conjecture paper, they continued the analysis and made it more refined. And the conclusion that they get is that this guy, so the thick subcategory generated by this guy contains a large trivial cyclotomic, contains some infinite sum of spheres p-adically completed with a trivial cyclotomic structure. Well, so let me not go into too many details about how you find a trivial cyclotomic spectrum inside there, but let me just say, where does the infiniteness come from? Where does the infinite? Well, the key is that we're kind of working p-adically. Implicitly, I mentioned all my cyclotomic spectra are p-complete. So you really want to think of this as sphere BZP, and then THH of sphere BZP. There's a sort of standard fact about THH of such function spaces to the sphere spectrum, which is that they want to be the same thing as the function space from the free loop space of BZP. This is kind of something that formally should be true for THH of a function space. That it's just THH of cochains on X should be cochains on the free loop space of X. And then LBZP is, morally speaking, it is ZP cross BZP, using the group structure on BZP. So this is like the pi1, and so if you fixed a base point, you'd be getting this, but you're not fixing a base point, so you also have a choice of base point floating around, and it's split. And then, so basically, THH sphere BZ p-adically is like continuous functions on ZP with values in S p-adically completed tensor SBZ. So that's kind of what's going on. Right, but now let's conclude. So we know that this term here lies in the thick subcategory generated by this guy. So this is a parenthetical remark. And this implies, by some finiteness properties of TC mod P, which, actually, the same paper of myself and Matthew Morrow, that fiber, so now you apply this TC functor to these cyclotomic spectra, that the fiber of TC RBZ to TC RBZ mod P lies in the thick subcategory generated by TCR mod P, tensor an infinite direct sum of copies of a sphere. Maybe I should put mod P on the outside. So basically, you can pull out this, when you calculate TC on the right-hand side, you can pull out tensoring with this guy, even though it's really big. So to conclude, so then it's enough to show that you have at least one infinite homotopy group for T, or you have at least one non-zero homotopy group for TC R mod PV1 V2 inverse. Because if you have at least one non-zero homotopy group here, then you'll have infinitely many infinite dimensional homotopy here, and therefore for anything in the thick subcategory, oh, sorry, it's backwards. This guy, I'm so sorry, it's backwards. This guy here lies in the thick subcategory. Yeah. Generated by this guy. Yeah. So since you see infinite homotopy here, it must come from, there must be some infinite homotopy here, and therefore we know this is finite, so there must be some infinite homotopy here. Mod V1 and with V2 inverted. But this is, yeah, and this is true by redshift. And miraculously, the course is done and I've finished on time, so thank you.
What was the essential role of TR in this group? Some of the steps doesn't work for TC, or?
No, the statements for, so we use the Quillen-Lichtenbaum property for TR, which is stronger than Quillen-Lichtenbaum for TC. Yeah. And it's important to have this stronger statement, is because that's what connects to the T structure on cyclotomic spectra. So having TR be bounded is equivalent to being bounded in the cyclotomic T structure, which gives you these finiteness properties for these cyclotomic spectra that arise.
Which is used in step 2.
Yeah, which is used when you want to go from the fact that they agree in the limit to they agree at some finite stage.
And they also do it for p equals 2?
Yeah, they also do it for p equals 2. And for higher height, yeah, it's not, I mean, I don't want to give the precise statement. They cook up some, yeah, they have to do things with these BPNs at higher height.
So it's again using algebraic theory of certain...
So, yeah, so you have some Z action on BPN, and they prove that for Kn plus 1 local K theory, you get that the Kn plus 1 local K theory commutes with the fixed points, but the Tn plus 1 local K theory does not.
Well, I think there's a silly question about the general argument of exchanging the V2 inverse with the mod V2 to the A. So we wanted to show, we wanted to find some infinite homotopy group after inverting V2 inverse. And you say it's enough to do it mod V to the A.
Yeah.
But I thought that the relationship between these two processes was that the periodic theory was given by taking some chunk of the mod V2 to the A theory and making it periodic.
Yeah.
But what if this chunk that we're looking at didn't contain the infinite homotopy group that we
Yeah, you're right. You're right. So that was a bit of a lie when I said that it works exactly like that. You discovered a flaw in the argument as I presented it. So once again, yeah, I'm not quite doing justice to the...
Okay, because you have only a certain range where it... This is what he said.
Yeah, that's
you
right.
said you make periodic some range,
Yeah.
but then if the infinite thing... Okay, this is the point, yes.
But, yeah. So what you really do is you don't make that reduction there. Once you have that, I presented it badly. You're absolutely right. So you're not supposed to make that reduction there. What you're supposed to do is run through the claim just looking at the cyclotomic spectra. So showing that for the trivial action non-trivial action is the same thing for the trivial action. And from that you deduce that when you take the V2 periodic homotopy of both, then they must be isomorphic in all degrees. And therefore trying to find some infiniteness on one side is the same as trying to find some infiniteness on the other side. So I shouldn't have done that step there. I should have done that step.
No, I
Yeah. Yeah.
But it is also the case that the infiniteness occurs in the chunk in the right. No, I have not.
Well, in the end, what you see is that this. In the end, it's the argument with cyclotomic spectra does give that for k bigger than or equal to 0, Tc of r to the p to the kz mod p v1 and then v2 inverse on homotopy. Well, so let's say mod v2 to the a. This is isomorphic to Tc r bz. Yeah, mod p v1 v2 to the a, and that implies isomorphism on V2 periodic homotopy by this Quillen-Lichtenbaum property. And once you know that, then you know that the problem of finding infiniteness in V2 periodic homotopy here is equivalent to finding infiniteness in V2 periodic homotopy here, and then that's what the rest of the argument delivers. So thank you, Matthew, you're absolutely right. I shouldn't have done that step, which was wrong. Okay.
So what's next?
What's next? Well, that's a great question. You'd think, yeah. What's next? Well, like I already mentioned that. The problem of whether you have hyperdescent for Kn plus 1 local K theory in this Devenitz-Hopkins tower for the full tower, not just the cyclotomic part, but for the full tower. In my opinion, that's an interesting question. In terms of chromatic homotopy theory, I feel that one of the most interesting issues is, so we know there's a difference between telescopic and Tn and Kn local homotopy theory. But there's also a bunch of things you could potentially define in between. And there's a question of how many of them are actually different from each other. So basically, for any choice of closed subgroup of the Morava stabilizer group, you can define something that a localization that lives in between them. So remember, Kn localization was kind of like hypercompleting in the whole Devenitz-Hopkins tower, but you could imagine just hypercompleting along certain directions. And the question of how many of those are distinct from each other and whether every possible thing that sits in between Tn and Kn is of that form, I find these also to be very interesting questions, which I have no clue how to attack. Yeah, what else?
What about Quillen-Lichtenbaum?
Yeah, Quillen-Lichtenbaum more generally than just for these BPNs and the homotopy fixed points for Z actions on such things.
Conjecture picture, what kind of things should have?
I mean, one needs to say what one means by regularity. So I should say that in the classical Quillen-Lichtenbaum for like Z1 over P algebras, we use this motivic filtration to analyze, and basically we reduce to an analog of the Quillen-Lichtenbaum property for motivic cohomology. There's some version of V1 in motivic cohomology, which when you invert it, you get a tall cohomology. And there's some version, you can write down a version of Quillen-Lichtenbaum there, and that was essentially the argument we gave. At higher chromatic heights, there's a version of the motivic filtration which was defined by Hahn, Raxett, and Wilson. And I think this is an active direction, is trying to kind of understand the higher chromatic analog of motivic cohomology and try to maybe phrase the requisite regularity property for Quillen-Lichtenbaum in terms of that motivic cohomology, analogously to how Bott and Matthew define some notion of regularity from the perspective of prismatic or motivic cohomology in mixed characteristic in one of their papers, and proved a sort of on the motivic level a Quillen-Lichtenbaum type statement. So yeah, those are interesting directions. I should have thought about it before. This is just off the top of my head. Yeah. Okay. Well, yeah. I should have thought about that beforehand. Yeah.
I have a rather naive question.
Yes.
If I take a spectra and if all the, well, say it's P local, and if all the Tn localization are trivial. Is the spectrum necessarily trivial or not?
No. So maybe I should say this is another interesting open problem. Sorry, not that. But no. So for example, if you take Fp, then Ltn Fp equals 0 for all n. So it's rationally trivial and it's bounded, so that when you make it periodic, it's 0. So here's another open problem. So there's a theorem of remember these LNFs which fit in a tower, and then there's the LNs which is like the LNFs except with Kn instead of Tn, the Kn instead of the telescopic. So there's a theorem of Hopkins and Ravenel that the sphere spectrum is the inverse limit of Ln of the sphere spectrum. So that the chromatic story, so it fails for Fp, for example, but when you take the sphere spectrum, it works. And now here's a question. Is it true with the telescopic version? Now this is very strange that this is not known, because the telescopic thing is a priori closer to the sphere spectrum. So this certainly maps there. Like the F version maps to the N version. So S is a retract of this guy. But we actually don't know whether the complementary summand vanishes. This is very, very strange. It's also strange because in this disproof of the telescope conjecture, in some further work that hasn't appeared yet, they go through and kind of show that it implies that there must be lots of, like basically this infiniteness phenomenon must already show up in the T2 local sphere, that you have some infinite homotopy group. And they deduce conclusions about the average growth order of the usual stable stems. So this failure of telescope conjecture is providing a lot of new elements in the stable homotopy groups of spheres, coming from height 2 from the telescopic perspective. But somehow you must eventually see them also from the non-telescopic perspective, but somehow at higher heights. And this is very confusing. And it feels like it should be a contradiction in mathematics, but apparently it's not.
No, it's the an isomorphism to okay, you know it's a retract. Okay,
you know it's a retract.
Okay, and using this you can construct
using just if you know there are enough classes in the T2 local sphere, homotopy class, if you know there are infinitely many classes than T2 local sphere, then you know that there have to be classes in the homotopy groups of spheres like infinitely high up, like many of them. And that gives you classes in homotopy groups of spheres, which you produce using telescopic homotopy theory. But in principle, non-telescopic version of everything should eventually pick up all the classes in the homotopy groups of spheres as well. So it's very, very confusing what exactly is happening here.
Okay, so there is a problem of how the order of growth of homotopy groups and estimate it in some way, from above or from below. So there are some papers on this using, okay, I'm not sure. I've seen something, I don't remember.
Yeah, there was a talk that Robert Burklund gave here. Maybe that's what you're remembering, or
yeah. So he gave a new progress on this constructing, showing that it grows fast enough.
Yeah, exactly.
This is a talk that he gave in 2023.
Yes, yeah. A year or two ago, yeah. All right, it looks like there are no more questions, so let's end it here. Thanks again, guys.